Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to solve one example related to the design of beam with compression flange laterally supported at intervals. To design the beam of figure, ignoring the self-weight and deflection check, the compression flange is laterally supported at point A, B and C. So we are given with the beam which is laterally supported at point A, at point C, at point B, and it is subjected to uniformly distributed load over this area, dead load and live load. A point load is acting at this point at a distance 7 meter at point C, and a point load is also acting at the free end of the cantilever portion. So we need to design this beam by using compact section with W shape or I shape. So first of all, we need to draw the shear force and bending moment diagram based on the factored load. So we can calculate the factor load by considering the factor 1.2D plus 1.6L. So these are the factor load acting on the beam, and corresponding to this factor load we can draw the shear force and bending moment diagram. So I am not going into detail of this shear force and bending moment diagram because we have already learned this, how we can construct the shear force and bending moment diagram in case of structural analysis. Okay, so from these figures from the shear force and bending moment diagram we can say that in case of portion AC, in the segment AC, the maximum bending moment is equal to 404, and in case of segment CB the maximum moment is 540, and similarly for segment BD again the maximum moment is 540. And shear force, maximum shear force in case of AC is 81, and in case of CB is 118, and in case of BD is 90. Okay, so here the MU maximum moment for portion AC and similarly for maximum moment for portion CB and BD are reported over here, and these are the unbraced length for segment AC, which is 7 meter, for CB it is 8 meter, and for cantilever portion BD it is 6 meter. So first of all we need to calculate the CB value for each segment, and to calculate the CB value for each segment we need to calculate the moment at the center, at the first quarter and at the third quarter, and we also need to calculate the maximum moment in that portion. So for that, if we see the portion AC, so for that we can calculate the maximum bending moment. We can see this diagram. So here to calculate the maximum bending moment in this portion, what we can do, we can multiply this reaction 81.56 multiplied by this distance which is x. For example, we say this distance is x, and we need to subtract the moment because of this UDL, which is 6.8 multiplied by x square by 2. So by using this expression we can calculate the bending moment at any point inside this segment AC, and we need the value of this moment at this portion at 1/4 point, and then at the center, and then again at the 3/4, and we also need the maximum value, and maximum value will be at point C. So these values are calculated over here. So we can see 81.56 into x, 6.8 times x square by 2. So maximum moment will be at point C at a distance of 7 meter, and MA at 1.7 meter mean 1/4 of 7, 1.7 meter distance. So its value comes out to be 132, and at the center at distance 3.5 meter its value is 243, and at point C its value comes out to be 334. So once we have all these moment values, so now we can calculate the CB value by substituting the values of these moments. So 12.5 times M maximum 2.5 times M maximum plus 3 times MA plus 4 times MB and plus 3 times MC. So by substituting these values, we can calculate CB, which is 1.49. Similarly, for portion CB, we need to calculate the maximum bending moment and maximum moment at 1/4 of the span, at the center, and at the 3/4 of the span. Okay, so here we can again go to the shear force and bending moment diagram. So we need the bending moment value in this segment from C to B. So if we see over here, we can calculate the maximum value, which will be at this point, which is 540, and then we need the value at, as this total distance is 8 meter, so we need the value at 8 meter from this spot, and then at 4 meter from this spot, and then at 6 meter from this spot B. So either we can use these triangles, and by comparing these triangles we can calculate the values, because we know this ordinate, and in between we need to calculate this much length. Or otherwise, the simplest way is, as we know the maximum moment at this point is 540, and by subtracting the area of this shear force diagram, we can get the value of bending moment at any location. For example, if we want to calculate the bending moment at a distance 2 meter, so in that case the bending moment will be 540 minus 2 times this 118. In 540 minus 2 times minus x time this 118.04, mean this 2 times this, we can get the area. So by subtracting the area from this 540, we can get the moment value at this location. Similarly for the other, because all this bending shear force diagram is negative, so we need to subtract these values. So for any value of x, we can calculate the bending moment value at any required location. So here if we see, the expression for moment is 540 minus 118 times x, and we need to calculate the bending moment at x is equal to 2 from the spot B, at x is equal to 4, and at x is equal to 6, and the corresponding values are calculated over here. So after calculating the values, we need to substitute in this the expression of CB to calculate the CB value. Again, it is 12.5 times M maximum, 2.5 times M maximum, 3 plus MA, 3 times MA, 4 times MB, and 3 times MC. So the value comes out to be 2.22. So for segment BD, which is the cantilever portion, so in case of cantilever portion, if the free end is unbraced for LTB, so in that case CB will be equal to 1. So now we have calculated the values of CB for all these three segments. Now we can make a table for MU, VU, LB, and CB for all the segments. So if we see for segment AC, MU is this one, VU shear force maximum is 81, LB unsupported length is 7, and CB is 1.49. Similarly for CB and BD segment. So after enlisting the value of moment LB and CB, now we need to decide out of these three segments which one is the most critical segment. And first we will design our beam for this most critical segment, and then we will check for the other segments. So we can decide this based on these three criteria: MU, LB, and CB. So if MU is larger, so it means the section will be critical. Out of all these three segments, the segment which has more MU will be more critical. So if we see here is 404, but these two have same magnitude. Similarly, LB, greater the value of LB, the strength of the section will be less. So this section has the segment has the largest LB, so it means its strength will be less. And similarly, if we see CB, So the lesser the value of CB, more critical will be the section. So we can give the preference, most preference to the CB, and then we also need to see this LB and MU. So if we see in this case the BD has the least value of CB, so it means there is the most probability that this BD will be the most critical segment, because these two have same moment but the difference of this LB is small as compared to the difference of this CB. So we can assume that this BD section is the most critical segment. So here I have explained the criteria how to select the most critical segment. So greater value of MU makes the segment more critical. A larger unbraced length reduces the member capacity. However, smaller value of CB is the more critical for a particular segment. So the effect of these three factors together determine whether a selected segment is actually more critical than the other segment. So actually all these three criteria determine whether the segment is critical or not. We need to see these three criteria simultaneously. The decision regarding which part of the beam is more critical for design depends on experience but may not always be accurate. If a wrong choice is made, if for example we have made the wrong choice, instead of BD, if I select that CB is the most critical, so what will happen? So if a wrong choice is made for this critical section, the procedure will correct itself, because only the calculation will be lengthy in such case, with the end result being always the same. For example, assume the portion BD. For this example, assume the portion BD is more critical and first design it. Later check for the other parts. So whatsoever section you have decided that it will be the most critical, so we need to design for that segment, and then we need to check for the other segment. So if we have made the wrong choice, so automatically for the other segment it will not be satisfying the requirements, so we need to revise the section, and ultimately the final section will be satisfying the requirement for all the segments. Okay, so now we have decided that the segment BD is the more critical, so we need to design for that segment. Okay, to select the section we need two factors, the D minimum and S required. So we select the section based on these two criteria. So first of all, D minimum, which is equal to L by 22 in case of buildings when A36 steel is used. So here L is 1500 and divided by 22, so the D minimum come out to be 682 millimeter. But here one thing need to be noted, that this 1500 is not the length of one segment. So it is the length of this span from here up to here, instead of from A to C or C to B, because this point C is braced laterally against the lateral bending. It is not braced for the vertical bending, and this D minimum is corresponding to the vertical bending. So if this D is corresponding to the vertical bending, so we need to consider this much span or this much span. So that's why we have considered this value of 1500, the total span 7 plus 8, 1500, 15,000. So depth for portion AB may be relaxed a little due to the presence of cantilever portion. However, the portion BD may have its own larger depth requirement. So once we have a cantilever portion, so in that case this support will become a continuous support. So the depth requirement for this segment will be lesser, because the load present on this side will reduce the deflection of this segment. So we can relax the depth requirement from this value of 682. Even the depth of the section is lesser than this 682, so it will be acceptable. Okay, for portion D, if we calculate the zx required, so we need to assume that the section is internally compact and there is no lateral torsional buckling. Once we assume these two criteria, then we can calculate the zx required by mu divided by phi b fy, and mu is 540 for this segment BD and fy is 250 for A36 steel. So the required section modulus is 2400 into 10 raised to power 3. So now we need to select the section based on these two criteria, the minimum 682 and Sx required 2400. So from the beam selection table, we need to select the trial section. So we can go into the beam selection table. So here we see our requirement of section modulus is 2400 and D is 682. So this section W250 into 167. So this section satisfies the criteria of Zx, and if we see its D minimum, so its D minimum is 289, which is significantly lower than this value. So we need to select some upper value. So if we see here, so the section has sufficiently larger value than this 2400, and if we see the D, so it is 603, which is less than this 682, but we can relax the value somewhat because as we have discussed that the section, because of this cantilever portion, the deflection of this segment will be reduced and we can relax the depth requirement. So from here we can select this section W610 into 92 and we can note down all these properties of the selected section. So here if we see, we have selected the section 610 into 92, and for that section LP is 1.75, LR is 5.33, LB is 6 meter, LM is equal to LP because CB is equal to 1. So once we select the section based on the beam selection table, so we need to check whether this LB is more than LM or less than LM. If the unbraced length is more than LM, so in that case the section which is selected based on the beam selection table will be inadequate. So for that we need to reselect the section based on the beam selection charts as given over here, and the section will be selected based on the MU and LB, and here CB is equal to 1, so we need not to divide it with the CB value. So we will use this MU 540 for segment BD and unbraced length of the segment BD, which is 6 meter. So if we see this chart, so here we have the point 540 corresponding to the moment 540 and the unbraced length 6 meters. So this will be our point. So we need to see the section on the right side and on the top. So the first section close to this is 610 into 125, but its depth will be significantly lesser than that of 682, which is required in this case. So to satisfy the depth requirement, we can select some upper section. So if we see this, the next section, which is 690 into 125, so it will have the depth close to the required depth 682. So we can select this section 690 into 125. Both sections have the same weight, but their depths are different. So our final selection will be 690 into 125 to satisfy the D minimum criteria. Okay, so from this table we can select the properties of our selected section 690 into 125 mean 5B MP value, 5B MR, LP, LR, BF, D, because we need these values to perform the capacity checks. So our trial section is 690 into 125, its actual depth is 78, which is less than 682, but it is within the permissible limits. LP is 2.64, LR is 7.67, BF is 77, and LM will be equal to LP as CB is equal to 1. And MP is 6, MP is 999. Actually, we select the value of 5B MP, which is equal to some value. For example, it is equal to A, and to calculate the value of MP, we need to divide this A with the 0.95B factor. So here if we see, the 5B Mn is 900. So once we divide it with 0.9, so its value will become 999. Similar will be the case for MR, because we select the value of 5B MR, so we need to convert it into MR value. Okay, after that we need to perform the compactness check. So the first condition is satisfied because it is a hot roll section, so web is continuously connected with the flange. And then we need to check for the BF over 2TF for flange and for web. So we can select these two values from the properties table for our selected section 690, and we need to compare it with the limiting value lambda p for flange as well as for web. So for the detail of these lambda p, you can refer to the video related to the example 1, that how we can select this lambda p for flange and for web, and their limiting values are 10.8 and 107 for A36 steel. And the BF over 2TF, which is 7.8 for our selected section, it is less than 10.8, so it's okay. And similarly for H over TW for flange, it's also less than 107, so it's also okay. So we can say that all these three criteria are satisfied, so our section is internally compact. Okay, after checking the compactness of the section, we need to calculate the flexural capacity. So for that, we need to compare the unbraced length of the segment with the LM and LR. So unbraced length is 6 meter and LM is equal to LP, which is 2.6 meters. So LB is more than LM, but it is less than LR 7.67. So once the condition is like this, so it means we are in the inelastic range. There will be inelastic lateral torsional buckling. So for that case, we can calculate the capacity by using this expression. And here CB is equal to 1, 5B 0.9, MP 999, BF slope 77, LB is 6 and LP is 2.64. So its value comes out to be 665, and it should be less than 5B MP, which is 899. So now we need to compare this 5B MN with the applied bending moment. So applied bending moment is 540 for the segment BD, and the capacity is 665. So it means the capacity is more than this MU, so it's okay. So our selected section satisfies the moment capacity requirement for segment BD. So after that, we need to perform the shear check, and that will be performed for the maximum value of shear. So for that, first we need to check this condition, that H over TW, if it is less than 63.4, so it means the CB value will be equal to 1, and we can calculate the nominal capacity or the design capacity of the section by using the yield limit criteria. And for that, the nominal capacity or the design capacity will be equal to 0.9 times 0.6 times Fy, which is equal to tau, and then area of web depth times thickness of the web. So it comes out to be 1070, and the maximum shear in the beam is 118. So the capacity of the section is larger than the applied shear, so it means it's okay. So for the segment BD, our final selection will be 690 into 125. So after that, we need to check whether this section, which is selected for BD, is adequate for the other segments AC and CB. So check for portion AC. So to check the flagellal capacity for that segment, we need to see the LB and we need to see the CB. So here LB is 7 meter and it is more than this LP, which is 2.62, and LR is 7 point something. So it means LB is greater than LP but less than LR. So we are again in the inelastic lateral torsional buckling range. So we can use this expression to calculate the bending moment capacity, which comes out to be 887, and in this segment, and this 887 is less than 899 mean 5B MP, and the applied bending moment is 404. So the capacity is more than the applied moment, so it's okay. So our selected section is also okay for the segment AC. So now we need to check for the portion CB. So here LB is equal to 8 meter, which is more than LR, which is 7.56. So it means we are in the elastic range. So there will be elastic lateral torsional buckling. Once there is a elastic lateral torsional buckling, the moment capacity of the section will be equal to Mn will be equal to FCR times Sx, and FCR is given by this formula, CB times pi square E over LB over RTS and JC Sx H naught. So this expression. So for that we need to calculate all these factors like RTS, JC, Sx, H naught, LB, RTS to calculate the moment capacity. So one by one we will calculate all these factors, or we will select these factors from the properties table. So first of all, Sx, the elastic section modulus, so we can select from the properties table for our section 690 into 125. Then we need to calculate this MP. We have already calculated this MP and MR, and similarly we have also selected the value of 5B MP from the table. Then we can select the value of JC and RY from the properties table, or we can also calculate the value of JC manually if we want to calculate, but these values are given in the properties table, so we can select its value. CB for this segment is 2.222. IY, the second moment of area about the y-axis, we can also select this value from the properties table, and the actual depth 678 millimeter, this is also from the properties table, and then this H naught. So H naught is actually the distance between the center to center of the flanges, from the center of this flange up to the center of this flange. So this will be equal to total depth minus f by 2 from this side and f by 2 from this side. So it will be d minus tf, thickness of flange. It will be tf by 2 and tf by 2. So in the previous video related to the nominal flagellal strength of the member, I have made a mistake that I write it d minus tf by 2. So that is wrong. It is actually d minus tf. So we need to correct that. So d minus tf, 678 minus thickness of flange, which is 16.3. So H naught comes out to be 661.7. So now we can calculate the RTS, which is IY H naught over 2Sx. By substituting the values, we can calculate its value, which is 64.66. And we can calculate this factor LB over RTS. So LB is 8000 divided by RTS. So after that we can substitute all these values in this expression, which is, this is FCR and this is Sx. So after substituting the values, we can get the nominal capacity or the design capacity of the section, which is 1137, and this design capacity should be less than 5B MP, which is 899, and here this 1137 is more than 5B MP, so it means the governing value will be 899. So this 5B MN will be equal to 5B MP 899.5, and this is more than the applied moment for this segment BC, which is 540. So this 899 is more than this 540, so it means it's okay. So our selected section satisfy the flexure requirement for the segment AC, CB and BD, and our final selection will be equal to W690 into 125. So this section will satisfy all the requirements for segment AC, CB and BD.